Thanks for the nice introduction by Professor Pierre Nuel. And let's get started. It's the first long talk in the morning and 19 minutes to the lunch. So let's fasten seatbelt. So hey everyone, my name is Wenxuan Zhao, and today I'm going to introduce you to prVis, a package which implements a novel method for visual dimension reduction. And the package is developed by Professor Norman Medloff, who is sitting right there, and a group of students, including me, Tiffany Jiang, and Robert Tucker in UC Davis. So just to briefly touch on what does visual dimension reduction do. So with the search of big data, we often encounter datasets with more than hundreds or even thousands of features. However, the original high-dimension data often contain measurements on irrelevant or redundant features. So dimension reduction as a means of denoising and feature extracting is a family of techniques that are applied during the analysis of such high-dimensional data. We sort of hope that our transformed low-dimensional data can remove noise but still retain the signal of interest, which can be instrumental in understanding the hidden structures and patterns in the dataset. So we can even further reduce the dimension to 3 or 2 in order to achieve the visualization of patterns within the data. And that is precisely what we are hoping to do here. So here is the basic outline of my talk. First, I'm going to talk about the motivation behind this package. So why do we need prVis? And then I'm going to review how the internal works, right? And we have also developed additional features and helpers to enhance the functionalities of the package. So in this project, we have 2 goals. The first goal is to discover unknown patterns, which is unsupervised learning, and we are using the Swiss roll dataset to illustrate that. And the second goal is to achieve separation between known components, where we do have labels. So if we have, there exists a nice separation, then there's hope we can develop a nice prediction model. So here's a partial list of the existing visualization methods. So there's like principal component analysis, T-distributed stochastic neighbor embedding, uniform manifold approximation, projection, and etc. So those methods are the methods we draw inspiration from, and we use as benchmark to test our methods. So this is our first example, and to illustrate the first goal. The first goal is to discover, we use the Swiss roll dataset to simulate it by Dynode Thuringen. The idea was to create a 4-component mixture and then map them to 3D with some smooth function. The key point is, what if we didn't know there were original 4 components? So we just mask this picture, and we only are given this picture. So, which means we only have this. And so we first applied the plane of PCA to the 3D data and plotted the first 2 principal components. So the resulting image is just a slice of that Swiss roll. So how many components do you see? So I would say 1, right? There's a continuous strips. So let us see how TSNE does. So the TSNE does achieve nice separation between data. So, but we do have about 5 or 7 separate clusters in this picture. And we know that we only have 4 components in the original dataset. So let us see how prVis does. So this is the result of the prVis transformation. So there seems like 4 components here, although there's overlapping here and there. And then we just unforget the group information and we apply the color to it. And this is the result. So how amazing is that, right? So this is our second example to illustrate the second goal. So we use the SPAM dataset. The SPAM dataset is a built-in dataset in the package kernel lab. and which has 57 predictors that predict whether an email is spam. Right? We know for sure that there are like 2 labels, whether an email is a spam or non-spam. Let us see how prVis perform. And we see a nice orthogonal separation between the spam emails and non-spam emails. By orthogonal, I mean that the spam group, the red points, spans over the x-axis, and the non-spam group spans over the spans over the y-axis. And so let us see how the UMAP does. So there's like overlapping between the spam email and non-spam email. And so does the TSNE as well. So just to clarify, we do not single out 2 extreme examples to make prVis look good. We additionally provide over 15 other examples to demonstrate prVis and directly compare it with other popular methods like UMAP, like TSNE. So please check out our big GitHub page for the prVis package, and more specifically, the gallery folder under this link for more examples. So you may wonder how it works, right? Internally, it first applies polynomial expansions to the original features and then applies PCA to the expanded features. In simple words, it expands the dimension and reduces it in order to capture the nonlinearity relationship in the dataset, the very functionality that the plain old PCA lacks. The idea can be traced back to 1969 from these 2 guys, Nediskin and Wilk. But back in the time, they lacked the computational power to do so, to actually implement this idea, especially the polynomial expansion part. Luckily, we have the package PolyReg, a package dedicated to use polynomial regression to perform regressions and classification tasks to do this part for us. So as I said before, this idea is simple and it's super fast. So in the spam example above, prVis runs 300 times faster than the TSNE on my Mac. So, but we have also illustrated the powerfulness of prVis through the previous 2 examples. In addition to the implementation of the big picture, prVis has provided features to help users explore the structure of the data. The name of the main workhorse function of the package is unsurprisingly prVis, and features are implemented as the options of that main function. Those features are added on the needs, based on the needs user will have in the real life, and we group those features based on their functionalities. So first, we have set of features to preprocess the data. The user can subsample, use the option unsubsam to subsample the data by specifying the number of rows the user wants. And when the original dataset does not have categorical variables, we can use an interval to partition one of the continuous variables into n intervals, and each of them corresponds to 1 label. And we can also use scale to scale the dataset to comparable scales, essentially. And I use the spam dataset as an example to illustrate the effect of the scale option. So although this is the non-scale version and this is scaled version. Although this version achieves some separation between the spam email and the non-spam email, this one does much better. After the pre-processing, we have options to specify the parameters of polynomial expansion operation and the PCA operation. The user can specify the parameters of the underlying polynomial regression. So these are the 2 tuning parameters to tweak the highest degree of the generated polynomial terms. As the degree does. And the max interaction degree, the option specifies the highest degree of the interaction terms. So for example, we have 2 features, x1 and x2. If we specify degree to be 2 and max interaction degree to be 1, the polynomial expansion procedure will produce x1, x2, x1 squared, and x2 squared. If the user specify both degree and max interaction degree to be 2, then it will produce one additional term, x1 times x2, as the interaction term. Okay. Admittedly, polynomial expansions uses a lot of memory, especially when the degree is high. To give you a sense of how fast the features get expanded, we originally have 57 features in the spam dataset. The number of expanded features goes up to over 1,000 if the user chooses to expand all degree 2 polynomial and interaction terms. And the number even goes up to 31,000 if all the degree 3 terms are expanded. However, if the user specifies the big memory option, the package then will force the package big useR to do the polynomial expansion that maps the expanded features that are too big to fit into the memory and fit it to the disk. So, and additionally, big useR provides the PCA operation directly onto the big matrix that's on the disk, producing little memory footprint. Thus, the user can either handle datasets with large number of features or expand the features to a higher degree, or both. So to speed up the PCA operation, the user can choose from 2 implementations of PCA in R, which is our prComp and rSpectra. And we found rSpectra are generally quicker than the prComp. And we can also use Mahalanobis distance to remove the outliers. And this plot is remove no outliers. So this one, there's one outlier intruding here and extracting, extending the x-axis to 3,000. And there are several outliers here as well. So after we remove 5% outliers, we obtain these scalable results. And we can also remove outliers by class, and which produce better results in this case as well. In the last stage, user can choose to save the output for future application. The output can also be used as an argument later passed to one of the helper functions. I'm going to demonstrate later. So this is a typical screen. So we load the data, we load the library, and we call the main function here. So we first scale the data as preprocessing stage, and we use rSpectra as our PCA method and removes 5% outliers by class, and we save the outputs to this file. So we also have helpers. The helper I'm going to introduce is colorCode. I use the PE dataset that records information about the programmers and engineers in the Bay Area to demonstrate how that colorCode works. Since there's no predefined labels, so I just use no option to generate these 10 black straps. And so I wonder, so how, what kind of meaning those 10 straps represent, right? So after calling prVis with no options, this is when colorCode comes into play. The user can specify an expression and use and see which portion of the data in the plot satisfies the expression he or she provides. The colorCode will load the saved output and process the expression. So for example, user may want to see which points have age less than 65 years old. So those are the black points in the left plots. And the user may want to continue the query looking for data points that have age less than 45 years old. And that's the middle plot. And the user wants to see 25 years old. That's the right plot. So we see how the black points shrink as the age goes younger, right? So we may wonder how the age correlates to the PC1, the first principal component. The user can also provide compounded expressions. User wants to see which data points have occupation 3, and denoted by color black, the lower 4 straps. Within that subpopulation, user may want to see which of them are male and which of them are female. After the querying, the user can see that the 2 black straps in the lower, in the left left picture are occupational tree and are male. And these two straps are occupational tree and female. The multiplication sign here is the logic and symbol for compounded expression. And that will that will conclude my speech. And this again is our GitHub page. Please check it out. Thank you.
Thank you.
And any questions are welcome.
Any questions?
Hi.
Hi. In many practical cases with working with data, there are variables that have a lot of zeros.
Mm-hmm.
Say 70% of zeros. How does the algorithm deal with that?
You can just use this method directly, and we tried it on the handwritten digits dataset. And that dataset is a lot of zeros. It's like 99% zeros, and it works as well. I mean, not as good as other methods, but it still can be. It's applicable.
Internal, how does it deal with the zeros?
Sorry?
Internally, how does it deal with the zeros?
Oh, okay. So it just again generate polynomial terms and interaction terms, and use dot products to multiply them together, and that's it.
So essentially, you add an indicator function, for instance, that interacts with other variables. Dummy 0, 1 function that says if it's 0 or it's
Can
not
you say
0.
that again? Sorry.
Okay, I can ask you later. Don't worry.
Okay. Thank you for your question.
First off, thank you. Thank you for the talk. That was very interesting. Here?
Oh, okay.
Here.
Sorry.
Can't you hear? No, I'm joking. So just to clarify, so the way you do it is you take the original data matrix, you add polynomial terms of the same axis you've had, and then on that you use PCA?
Yes, exactly.
So some small questions about that. First one is it just straight on polynomial, or do you use some orthogonalization or something like that of the values?
Orthogonalization?
Like try to make it so that the higher polynomial terms are orthogonal to your original ones or something like that. Is that something that is relevant?
No, but no.
Okay.
We use PCA to do that, right? The PCA can produce orthogonal independent vectors and all that.
And the second question, do you think there is value in alternative manipulation, for example, log or other power transformation than just polynomials, like using logarithms or stuff like that? Would that also make sense under your framework?
Yeah, that's definitely doable, and yeah, we will look into that later. Yeah,
Okay.
That's some features we can add later.
Okay. Thank you. It's very interesting.
Thank you.